We are continuing with finding the area between two curves, and the example for this video is find the area of the region bounded by, and the first equation is y is equal to 2 minus x squared, and the second one is y is equal to x. The primary difference between this problem and the ones that we've been focusing on so far is there is no left and right bound explicitly defined within the problem. So to answer this question, we need to integrate from a to b, f of x minus g of x with respect to x. So what we don't have in the problem is that a and b value. So to get a feel for what's going on, I'm going to draw a rough sketch of this. The first equation, y is equal to 2 minus x squared. X squared is your basic parabola. Flip that down, bump it up 2 units. So its vertex is at 0, 2. It's standard width, so we can use the shortcut of over 1, down 1, over 1, down 3. Mirror image on the other side. So we're looking at the rough sketch of more or less that right there. The second equation, y is equal to x. That's a linear. It has a y-intercept of 0, slope of 1. So it's looking roughly like that. So the left bound is going to come from that endpoint. The right bound is going to come from that endpoint. And we're looking for that area bounded by the two curves, or that shaded region. All right, now it's possible that they already gave you a graph. That graph is very accurate, and you can identify the coordinates of those endpoints simply by inspection. Maybe the graph that you sketched by hand was accurate enough where those endpoints could be determined. Maybe you decided to take a traditional paper-pencil algebra approach and solve that system algebraically to get those points of intersection. All those things I just mentioned are valid to do, and if whatever fits the particular problem, then use that particular strategy or that method. What I'm going to focus on for this video is using a graphing calculator in order to accomplish most of this work here. So I already have my two equations in the y equals screen. I already set up a window so I can nicely see what I want to see. And we get the graph that looks pretty similar to what I sketched out by hand. So we need the coordinates of that left endpoint. We need the coordinates of that right endpoint. So second, above the trace to get at the Calc menu, the intersect option is choice number 5. It's going to ask us the three questions rather. First curve, second curve, guess. And that gives us an intersection point of -2, -2. Same set of keystrokes for the right intersection point. That gives us an intersection point of 1, 1. So going back to our formula for a moment, those a and b values are going to represent those x coordinates. So we're integrating from -2 to +1. The f of x is referring to the top curve. That's the parabola. So as I have it in my calculator, that's my y1. The g of x refers to the bottom curve, which is the linear. As I have it in my calculator, that's my y2. And integrating with respect to x. So I'm going to quit out of the graph. I am going to go to my home screen, math, get the FNINT function. You're integrating from -2 to +1. And we could type in those functions as is, but if we already have them in the y equals screen, much more efficient thing to do, alpha f4, y1 minus alpha f4, y2 with respect to x, and we get an area of 4.5. As always, if you get a decimal that's not a nice clean decimal like 4.5, make sure that you're following the round off instructions on whatever the assignment or the quiz or the test is. Also, as a reminder, one of the disadvantages of using technology, sometimes you don't get an exact area, you get a decimal approximation for some irrational expression, and that's just the nature of the beast in terms of using the technology in order to get that particular answer. So in conclusion here, the difference between this problem and the ones we've focused on so far, we don't know explicitly that left and right bound, so we need to find those. Once we find those, the problem pretty much plays out the same as what we've already done prior to this particular video.